I will speak today about our recent experimentation on using our machine learning tools combined with the so-called high-dimensional model representation to try to not only be able to machine learn the data from sparse sets, but also to reveal the relevance of different combinations of variables. As a matter of general introduction, machine learning is, of course, today a very big deal. It's used in all sorts of settings. It's used specifically in quantum chemistry and related areas. First of all, directly in a way of producing the desired property. For example, various descriptors of catalytic activity as shown on this example from a recent review, in which case you would be defining a set of descriptors and then essentially shooting through directly for the properties or the quantities that you want. And various workflows have been proposed to that effect. What interests us in the first place is a somewhat different use of machine learning, whereby machine learning is used to improve the modeling methods themselves, be it methods which rely on interatomic potentials or on DFT, which enter these various computational workflows, which may or may not depend on machine learning in the bigger scheme of things. Interatomic potentials are, of course, a well-oiled research area today, which has largely moved, I would even say, beyond science and towards software engineering. Another area where we are in particular interested is using machine learning to enhance not just DFT, but specifically orbital free DFT. And the reason we are looking at orbital free DFT is because we are looking for a way towards genuine large-scale ab initio calculations of material. And when I say genuine large scale, it means that I want to do a million atom calculation, not by loading a supercomputer for a month, but right on my desktop. And if I want to repeat that calculation 10 times, I can. And orbital free DFT is pretty much the only proposition in the ab initio space that would allow us to do that. A well understood problem in the orbital free DFT is, of course, the construction of the kinetic energy functionals. And that is an example which I'll be showing in today's talk. We do work beyond the kinetic energy functionals, specifically on the constructing of orbital free DFT suitable pseudo potentials, which need to be local in the case of orbital free DFT. This part will not enter this talk for the lack of time, but this is a general setting where we want to enhance orbital free DFT methodology using machine learning. One of the things which I will specifically focus on in this talk is how do we go about alleviating some of the disadvantages associated with a black box nature of commonly used machine learning techniques, and to try to derive some sort of insight, which is typically available with intuition rather than black box based methods. Machine learning is, of course, not a panacea. It comes with a set of pros and cons. The great advantages are generality and black box character, pretty much of all stable machine learning techniques, and therefore we can be free of the bias imposed by some physically motivated learning, especially non-parametric machine learning techniques allow to do that, including general Gaussian process regression, which I will also be mentioning in this presentation. Machine learning can make use of our implicit information, some knowledge which is somehow distributed among the data points, but which is very hard to explicify, to pronounce. And one of the greatest advantages is, of course, machine learning tools are now widely available and can be literally used by anyone with minimal training. Unfortunately, there are disadvantages, which include the notoriously bad extrapolation of not just machine learning based techniques, but pretty much all black box based techniques. Therefore, some things need to be done to ensure that extrapolation behavior is right, including definitions of variables, etc. And typically, machine learning techniques, as any black box techniques, require more data than physically motivated models to build a good approximation. And this is important, especially in high dimensional spaces, where the data are always sparse. It doesn't matter if you add another million data points in a 20-dimensional space. the density of sampling will still not budge. And as I mentioned before, there is limited interpretability or insight, physical insight, as people like to say, with many of the black box techniques, including the common machine learning techniques. What we have been trying to do is to develop methods which would, in a way, harness or use by way of building blocks, bricks, existing machine learning tools, which can be used for their black box nature in their comfort zone, and yet in a way which would allow us to work with extremely low data density, even in high dimensional spaces, as well as getting at least some insight from these techniques. The approach that we like in particular is the so-called high dimensional model representation, which sounds fancy, but in reality, it's a misnomer, by the way. The concept of HDMR was introduced around 1999 in Herschel Ravitz's group at Princeton. The concept is, of course, similar to the concept of the multi-body representation. It's an expansion over the orders of coupling. Specifically, the flavor of HDMR that we are using, which is the so-called RS, random sampling HDMR, which allows constructing all of these coupling terms from one and the same arbitrarily distributed set of data, goes back about 100 years to the analysis of some of the analysis of variance technique. So this is really not new. This is a representation of a multivariate function f in orders of coupling taken to full order. This is an exact representation. There is no approximation made. You begin to approximate when you start cutting this expansion at some highest order coupling, small d, which you consider. We introduced an extended approach of this HDMR technique, whereby we represent a capital D-dimensional function f with a bunch of small d dimensional component functions f blue here, which are all lower dimensional. And the reason we can use this simplified representation is precisely because it's facilitated by the use of machine learning to construct this component functions f blue. In general, such representations of multivariate functions with lower dimensional terms are extremely advantageous. First of all, the lower dimensional terms are easier to build. These are low dimensional functions, therefore they can be built from fewer data without overfitting. Even in high dimensional spaces with extremely sparse data, you can define these lower dimensional functions, which are very well defined. They are easier to use. Think, for example, of integrating a 20-dimensional function, which is a nightmare. If you represent it with a sum of lower dimensional terms, it becomes much, much easier. And importantly, this kind of representation, it does provide element of insight, because different magnitudes of this component function of these terms will inform you of the degree of importance, not just of individual variables, but of different combinations of variables. By the way, the 100-year-old ANOVA decomposition was meant to do exactly that, to understand the relative importance of different combinations of variables from the statistical perspective. One thing which I would like to highlight is that the representations that we are using is not to be confused with the so-called N-mode or multi-mode type of representation. Ove called in his talk also used the HDMR language. Yesterday he called it for what it is. The N-mode representation, often used in physical chemistry, is what Herschel Rabbis called cut HDMR, in which case these component functions are slices of the full dimensional function passing through an expansion center. And the determination of this component function would then require as many data sets as there are component functions, which is combinatorially explosive. What we are using is what Herschel Rabbis called random sampling HDMR, and in which we determine all of our component functions from one and the same data set. The functions that we build are not the functions of the N-mode representations. They are determined all from one and the same data set. And the use of machine learning has certain advantages to do that, to build these types of representations. Both the RS and the HDMR language is a misnomer, really. A random sampling should have been called arbitrarily sampling. And high dimensional model representation is really a low dimensional model representation, because we are representing a high dimensional function with lower dimensional terms. But the language has been set, and we will go by the Herschel Rabbis' language. Now, as I said, we are able to ditch the lower dimension. We don't have to, but we can in principle ditch the lower dimensional parts of the representation and focus only on the highest of the terms of the highest dimensionality small d that we're willing to retain. In which case we will use machine learning techniques, be it, for example, neural networks or Gaussian process regressions, which I will be using specifically in this talk, to construct these lower dimensional terms. Why is it advantageous to use machine learning to construct these lower dimensional terms? Because when you use machine learning, you can, specifically in the case of RSHDMR, you facilitate the construction of the terms greatly. In the original random sampling HDMR literature by Herschel Rabitz's group in particular, these functions, the mathematical expressions for these functions, are capital D minus small d dimensional integrals. These are very high dimensional integrals and they are debilitating. When we switch from essentially from computing those integrals to simply fitting our machine learning based representations of these component functions, we ditch that entire set of problems outright. The way we do it in practice is that we would define a neural network or a Gaussian process representation for each of the component functions, and then we will build the sum, and we would cycle for all component functions, fitting one at a time until we converge the representation. The version where component functions were neural networks we presented already 10 years ago, and recently we have been playing with component functions which are represented with Gaussian process regressions. And the reason we do that, I will show in the next couple of slides, and that includes elements of insight. Another advantage of this kind of representation is that it allows, in principle, breaking this combinatorial scaling of the number of terms with both the dimensionality of the term and the dimensionality of the original space. We can very simply define linear combinations of the original variables. And in these new variables, xi, capital I, or x prime if you want them, we can then play at will with the term, with the number and the dimensionality of terms in the representation. And we can completely break this combinatorial scaling of this representation with different dimensions. Already 10 years ago, we have used this kind of approach with neural network-based terms to build the first ab initio-based potential energy surface for a polyatomic molecule surface reaction, which considered all molecular degrees of freedom. And we were able to do it with an ab initio computed data set with a density of less than 2 data per degree of freedom. As I said, this low dimensionality of terms allows us to work with sparse data. Recently, we've been using Gaussian process regressions for these terms. This paper, which has been just accepted to computer physics communications, gives some examples of the applications also beyond chemical physics or beyond quantum chemistry. So this is an example of, for example, what one can get by fitting simply as a test case a potential energy surface of water in bond coordinates to 500 data points, whereby simply by defining different linear combinations of the terms, we can see that already at the 2-dimensional HDMR level, at the level of second order coupling in this novel coordinates, we can significantly improve the global root mean square error of the potential simply by redefining these linear combinations without formally going to a third-dimensional term in our newly defined coordinate. Gaussian process regressions, which I have now mentioned several times, we are using Gaussian process regressions now to build the component functions of this kind of extended version of random sampling HDMR. A quick couple words about Gaussian process regressions. The Gaussian process regression can be understood very rapidly in this way. Imagine you have a function, this blue function sampled in a generally multidimensional space with samples xi. And you know that the values of the function f you're trying to represent at different xi, they correlate with certain covariance functions that you define, k of x1, x2 in this case. One builds the matrix based on these values of the covariance function k in this way, where this k, x, xi, xj is basically pairwise values of the covariance function at all of your training data. And the prediction for the value of the function kind of between at any other location in space is computed from the inversion of this matrix K, the vector listing all the known data points, Tn, as well as a vector which encodes the values of the covariance function between the new data point of interest and all of the known data points in the space. That vector is labeled here as K star. One of the advantages of GPR is that it can also provide the estimation of, I want to take it in bracket, the error. It's not really the error bar, it's the variance of the estimated expectation value of the functions that you are trying to reproduce. There is a lot to say about the relation of this object to the actual error bar that could take a separate talk. Maybe I will give it in a future conference. But in certain cases, this expression can be used as an error bar, in certain cases only. Now, these functions Ks are typically taken as one of the Maton family of functions. Here is a great kind of generic expression for the Maton family of covariance functions pulled straight from this Wikipedia page, which you can click and have a look at them. For particular values of of nu, for particular values of nu, this expression collapses either in a Gaussian-like or so-called square exponential function, which people using Python will recognize as the RBF kernel, or functions which are, for example, Maton 3/2, Maton 5/2, which actually look like the radial distributions of the wave function of a hydrogen atom, quite frankly. What we are interested in here is that when one uses, for example, the radial basis function type kernel, which is essentially an exponential type kernel in this GPR method, and then one optimizes the hyperparameters of this kernel, which in the case of the exponential kernel, basically the most important hyperparameter is the length scale of the kernel. In this case, the optimal length scale gives us information about the importance of that particular variable, and that is the basis of the so-called automated relevance determination. Using the RBF kernel with Gaussian process regression can easily tell you the importance of the variable, because when L becomes very, very high, the influence of the change in that variable becomes smaller and smaller and smaller. So if the L is taken to infinity, that variable basically doesn't matter. This is the basis of automatic relevance determination. Now, before I talk about how we go a little bit beyond automated relevance determination, I will introduce the problem which will be actually befitting. I was talking about the use of machine learning to fit kinetic energy functionals for orbital 3 DFT. In a previous talk, we had our presentations about exchange correlation functionals fitted with neural networks, which were convolutional type of neural networks. What we do not use convolutional neural networks. We instead focus on the construction of descriptors. When you do machine learning, for whatever application there may be, the definition of the descriptors, the finding good descriptors, is 80% of the success. If you find perfect descriptors, the rest of the problem evaporates. The descriptions that we like are the terms of the fourth order gradient expansion of the kinetic energy. The gradient expansions of the kinetic energy are very well known. Expansions of up to the sixth order, in fact, are known. There are analytical formulas for them. We do not use the sixth order expansion. We use the fourth order gradient expansion, which is given here in this somewhat cryptic form, where P and Q are the so-called reduced gradient and Laplacian of the density. They are scaled to satisfy the so-called scaling relations exactly. We don't always use the scaled versions, but sometimes we do. And we were able to numerically converge all terms of the fourth order gradient expansion. And we use the terms of the fourth order gradient expansion as descriptors. And if you have sufficient number of derivatives of sufficient order, you in principle shouldn't need to use a convolutional neural network. You just use a conventional machine learning technique using all those derivatives as your descriptors. And that is what we did. And when we use a neural network, we found that in this space of descriptors, using a relatively small neural networks with a dozen or so neurons, we were able to represent to reproduce the Kahn-Sham kinetic energy density rather exactly for several materials, including, for example, silicon, which, as an example of a semiconductor, is still somewhat problematic with orbital 3 DFT. What we, just as an aside, before we move on to Gaussian process regressions, what we also found is that, for example, we could fit very well kinetic energy, Gaussian kinetic energy densities of individual materials with a single hidden layer neural network, which is of course a universal approximator already at the single hidden layer level. But to reproduce well the kinetic energy densities of several materials simultaneously, we needed to go to a multi-layer neural network, and that ultimately has to do with the very unpleasant distribution of the data in the space of descriptors. If I have a few minutes in the end, I will give examples of those nasty distributions. Now, we also performed in the similar kind of space of descriptors, we also performed Gaussian process regressions of kinetic energy densities of different materials. Some of them are shown here, aluminum, magnesium, and silicon. This is the example of the correlation, the kind of correlation plots that we get when regressing kinetic energy densities with Gaussian process regressions for to the data computed with Gaussian DFT for all of these three materials at also a different level of strain. So this is a combined data set. There is about 1 million data points here. So this small number of outliers, they are really, really a small number compared to the entire data set. Another thing that we do is, knowing how difficult it is to optimize things with orbital 3 DFT, we look directly at the property having to do with the quality of the potential between the atoms. We look at this approximation of the bulk modulus, and we try to make sure that after we have fitted the kinetic energy density, when we replace the constant kinetic energy density with our fitted kinetic energy density, do we reproduce this bulk modulus-like quantity, which we kind of do, right? So this is also important. In this particular case, we also found that beyond the terms of the fourth order gradient expansion, it was extremely useful to add the, as a descriptor, another variable, which is the product of the density and the effective potential, which is also computable without recourse to the orbitals. So this is a legitimate descriptor. This is an example of when I said that in this problem, data have an nasty distribution. This is an example of what kind of distribution of data we are dealing with. So this is example, for example, P with your scaled Laplacian, scaled gradient. Q is your scaled Laplacian. These are very, very nasty, extremely uneven distributions, which is why things like multi-layer neural network are useful, for example. Going back to the automated relevance determination and beyond, I've mentioned before that with Gaussian process regression, the length scale of the kernel can serve as a piece of information about the importance of that particular variable. Well, if one uses a Gaussian process regression not by itself, but to represent lower dimensional component functions of the random sampling HDMR, then we have a new possibility. We have a possibility now at looking at the length scale of the kernel used to represent each of these in general multivariate, albeit lower dimensional component functions. And similar to ARD, we can see that after we have optimized the length scales of all of these component functions, we see that some of these terms return to us very large L. And that means that those terms basically don't matter. And if they don't matter, it means that we have a way to tell which of the combinations of variables matter and which of the combinations of variables do not matter. Not individual variables, but combinations of variables. Why is it important? A, if you know in a highly dimensional space which combinations of 2, 3, 4, etc. variables are important, you can now take those combinations and go back home. How many minutes do I have?
Sergei, can you just 1 more minute?
Okay.
We need to leave time. Yeah,
this is pretty much, we are at the end now. So you can now take those combinations of variables which you know are important and move to any other method. Does not have to be machine learning. It can be writing formulas back home at your desk and work with those combinations of variables to build formulas for kinetic energy density or even for kinetic energy directly. Another advantage of this approach is that if you know that some combinations of variables are unimportant, you can remove them from the overall expansion. And if you remove them from the overall expansion, you have again pretty much broken the combinatorial scaling of this HDMR type of expansion. We found, for example, that many of these terms are actually not needed. So once we have pruned them, we can now we can easily work with dozens or hundreds of these terms, but maybe not with 10,000. And what we found is that the majority of these terms actually gradually disappear, especially as you increase the small d that you include in your HDMR expansion. I will skip this last, just as a quick aside, the HDMR structure allows you to also impute the missing values of variables in your data set, which is a separate, super important problem in real life applications. We described a little bit in this paper how HDMR GPR can help resolve it. No time to do it today. So to conclude, we like to build representations of multivariate functions with lower dimensional terms. This allows us to work in principle with extremely sparse data and determine all terms from one and the same data set. From one and the same data set, there is no and no, there is no cut HDMR. We can build terms with neural networks of Gaussian process regressions. The HDMR structures allows us to get insight, including understanding which combinations, not individual variables, but combinations are important. One of the applications we look at is construction of kinetic energy functionals for orbital free DFT, where we are seeing some progress. We also work on local pseudos with machine learning, but that's a separate story. Now, before I shut up, I would like to thank people who were on the papers, which are from where the results I was showing today. Taka Carrington from Queens, my former postdoc Pavlo Golub, who's now in Prague, Owen Rang, my postdoc, Mohamed Alizi, summer intern last summer, Dmitry Wojciechowski from PureFacts Inc. And with that, I thank you for your attention and sorry for being a little bit over time.